Well, good morning. This is the first lecture on refractory compositions. We've gone over the basics, crystal bonding, crystal structures, glass structures, and phase diagrams. So we'll start with silica refractories today. And each one of these compositions, refractory compositions, will discuss the raw materials, the phase diagrams that are relevant, how these materials are processed, the resulting microstructures, and then some of the key properties. So the raw material for a silica refractory is quartzite, just quartz. And I've listed two chemistries here. The first one is 98.6% quartz. The other one is more pure, 99.7. So these refractories have to be high purity in order to have high melting properties. So a conventional silica refractory has up to 1% impurities. And then a super duty, which would be a higher temperature refractory, is usually going to have less than 0.5% impurities. So this would be a super duty silica refractory, and this one would be a conventional refractory. So alumina, iron oxide, calcium and magnesium oxides, and the alkalis, sodium and potassium, are the primary impurities. There's also fumed silica and fused silica. Fumed silica is a very fine particle size silica used a lot in castable type refractory systems for producing higher density castables, and also is very reactive with alumina to form mullite. So there's a low purity fumed silica and a high purity fumed silica. The high purity is 99.5% silica, and the lower purity is about 96.8% silica. And the same impurities are present: alumina, iron oxide, calcium and magnesium oxides, and then the alkalis, sodium and potassium oxides. Fused silica is a glass. It just, of course, melted at high temperatures. And the fused silica is usually a high purity, and this one's 99.6%. So there's a synthetic fumed silica, and it's really a pyrolysis process. You have a high temperature flame. You inject silicon tetrachloride. The flame's at about 1500 degrees C. And then the product is SiO2 and 4HCl. So the particle size is pretty fine, 5 to 50 nanometers. So you can make synthetic fumed silica. And another way of making synthetic fumed silica is it's a byproduct when you make silicon metal or other ferrosilicon alloys. So silicon metal is made by heating quartz and carbon at the same time. The carbon reduces the quartz to silicon metal, but there's a gas generated, and that's in the form of silica. So that very fine particle, silica, is collected and is known as fumed silica. Particle size is on the order of 150 nanometers. So you have a fumed silica from a decomposition reaction, and you have a fumed silica as a byproduct. And again, these are used extensively in castable type refractories. They're highly reactive fine particles. Fused silica, you basically heat quartz and you melt it. So this is an induction furnace. It's a high temperature furnace. and they usually run in vacuum or inert atmospheres. So these are the water-cooled coils that are used in an induction furnace, and you just melt quartz, and then you end up with fused silica. And when we talk about glasses, if you have a silica glass, 100% silica, it's not going to crystallize back into cristobalite or trinamite. It's very hard to crystallize, so you end up with a fused silica glass. You can also drop a powder into a high temperature flame, and that produces a silica glass also. So simply melting in a crucible or melting in a high temperature flame, you make a silica glass. The silica glass has a very unique property of low thermal expansion, extremely low thermal expansion, but it has a low use temperature. It is a glass, and it will crystallize above 1,000 degrees C. So it has limitations. So when you apply heat to quartz, the silica exhibits these polymorphic transformations, and we mentioned a displacive transformation and a reconstructive transformation. So again, a displacive transformation, you're just distorting the crystal structure, you're not breaking atomic bonds, and it's a very rapid transformation. In a reconstructive transformation, you're altering the crystal structure, you break atomic bonds, and it's a very slow reaction. The kinetics are slow. Silica melts at 1723 degrees C. So it's one of the lower melting refractory materials. And I showed this a few classes ago. Just as a review, here's an ordered crystal structure, and that's A, and B and C are disordered, displacive transformations, and then D, you form a new crystal structure. So in B and C, you're just shifting the bond angles, the structural units, this cube, 4 ions at the corners, 1 in the center. The bond angles are just shifted, but in the reconstructive transformation, you're breaking and reforming the bonds. So silica exhibits both displacive and reconstructive phase transformations. And this slide summarizes all those transformations. So you start out with quartz. It's alpha quartz, the low temperature form, and you heat up quartz. And at 573 degrees C, there's a displacive transformation. So it goes from alpha to beta quartz, and there's a 0.9% volume expansion in that transition. And if you take quartz and then you heat it to a high temperature, the first reconstructive transformation is for tridymite. So thermodynamics predicts that 867 degrees C, this reconstructive transformation should take place. But you also have to consider the kinetics. Thermodynamics just tells you the equilibrium situation, what should be at equilibrium, but the kinetics tells you how fast it gets there. So the kinetics are really slow here. So really 1200, 1400 degrees C, you go from quartz to tridymite. That has a very large volume increase, 14.3% volume increase going from quartz to tridymite. If you go from quartz to cristobalite at a higher temperature here, 1470 degrees C, another reconstructive transformation, there's an even bigger volume increase, 17.2%. These large volume increases really can disrupt the structure. So if you have tridymite and then you heat it up, you go from alpha to beta 1 to beta 2 tridymite. those displacive transformations are at 105 degrees C and 160 degrees C. And that has a 0.4 volume percent expansion. And then if you have cristobalite, it goes from alpha to beta cristobalite in this temperature range, 200 to 270 degrees C. And there's a bigger volume expansion than with tritamide, it's 2.8%. So the ideal microstructure for a silica refractory, you start out with quartz, you convert it all to tritamite, which has the lowest volume expansion for the displacive transformation. In reality, you end up with both tritamite and cristobalite, but you want to remove all the quartz. You want to convert all the quartz to either tritamite or cristobalite, preferably tritamite, because of the lowest volume expansion. So when you do the reconstructive transformations, you're eliminating these large volume increases by eliminating the quartz. So the common stable polymorphs, you go from alpha to beta quartz at 570 degrees C. Quartz to tritamite, the reconstructive transformation, theoretically 867 degrees C, but the kinetics are quite slow. So it's more like 12 to 1400 degrees C. To tritamite, beta 2 tritamite to beta cristobalite, 1470 degrees C, it's reconstructive. And then eventually, if you reach 1723 degrees C, it melts and you form a liquid. So there's also metastable polymorphs. So if you're forming beta 2 tritamite at high temperatures and you cool it down, theoretically it goes to beta 1 tritamite and alpha tritamite, but it could be metastable. It may not take place. And the same thing here with cristobalite. If you're at high temperature, you have beta cristobalite and you cool it down back to room temperature, it may be metastable in the beta cristobalite form. It may not transform. So this summarizes the phase changes, the temperatures where the changes take place, the linear and volume changes with those phase changes. So 117 to 163 degrees C, you go from alpha to beta 1 to beta 2 tritamite. The linear change is 0.1%, 0.17%, and the volume change is about 0.5%. In this temperature range, 200 to 210 degrees C, you go from alpha to beta cristobalite. The linear change is 1%, and then the volume change is about 2 to 2.8%. And then 573 degrees C, alpha to beta quartz. Linear change is 0.26 to 0.5%, or 0.86 to about 1.3 volume percent. These are all displacive transformations. Beta quartz to beta 2 tritamite, again, 870 is predicted by thermodynamics, but it's too low for kinetics. 5.55 linear change, that's percent, and about 14.4 volume percent change. And then at 1250 degrees C, beta quartz to beta cristobalite, 6.6 linear change and 17.4 volume change. And then a few other ones here, beta 2 tritamite to beta cristobalite at 1470 degrees C. There's a 1% linear change. At 670 degrees C, beta 2 tritamite melts. The melt has a volume change, about 1%. And at 1713, beta cristobalite melts about a 0.1% volume change. So those are all the different types of crystal transformations, whether they're displacive or reconstructive. And these are the different crystals that are possible: alpha and beta quartz, alpha beta cristobalite, and alpha beta 1 beta 2 tridymite. These are the corresponding crystal systems. We talked about the different types of systems before, and then their lattice constants A, B, and C, depending on what type of crystal system, and then their specific gravities. So you can see quartz and the alpha form is 2.65. That's grams per cc. Then when you transform to beta quartz, it's 2.49. So it's a lower specific gravity. That's where you have that volume expansion. And the same thing, you can look at alpha to beta cristobalite, 2.33 to 2.21. So there's a density decrease or a volume increase. And I showed this before, but I just put it on here again. The different crystal systems: cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, rhombohedral, and then hexagonal primitive. So what happens when you take SiO2, the mineral, which is quartz, you apply heat? I mentioned you want to end up with basically 100% tridymite, because once you form tridymite, you get rid of that large volume change going from quartz. When you heat and cool tridymite, you have the lowest displacive transformation change. So it's only linear change, volume change of 0.4%. But you're usually going to have a combination of tridymite and cristobalite. You're going to get rid of these large volume changes when you eliminate the quartz, but you're still going to have your displacive transformations for tridymite and cristobalite. So going from quartz to either tridymite and cristobalite, these are slow reconstructive transformations. The kinetics are quite slow. So what you usually do when you make a silica refractory, you add a mineralizer. So lime is a mineralizer. And basically what happens, it enhances the transformation of quartz to tridymite and cristobalite. So a small lime addition, I have 2% here. It's usually between 1 and 3%. So you add lime to quartz, it forms a small amount of liquid. So that liquid dissolves the quartz, and the quartz reprecipitates as either tridymite or cristobalite. So tridymite and cristobalite crystallize from that liquid phase. So the mineralizer really speeds up the transformation from quartz to either tridymite or cristobalite. So you're controlling these transformation rates with the addition of lime, and you're controlling the volume changes. So quartz has a density of 2.65, that's grams per cubic centimeter. Tridymite, lower density, 2.26, and cristobalite, a lower density than quartz, 2.32. So going from quartz to either tridymite or cristobalite, lower densities, higher volumes. So when you convert all the quartz, ideally you don't want any quartz left. You end up with a combination of tridymite and cristobalite, and you eliminate those large volume changes.
Excuse me, I have a question about that.
Okay.
Is that that volume change is so large that in practice, is it destructive in nature? I mean, does it break the material down into, cause fractures in the material to break it down into a powder or something like that?
I'll go over the heating schedule. So when you start out with quartz, you have to heat it very slowly over many, many days to avoid the disruption of the structure.
Okay. Mm-hmm.
So when you have the actual silica refractory, after you convert it all to tridymite and cristobalite, you only have the displacive transformations. So you still have to be careful on the heat up in practice. They're using coke ovens and glass tank roofs. So you have to have a slow heat up even after you have tritamite and cristobalite to prevent any fractures. But you never want quartz present in a silica refractory because that's going to transform to tritamite and cristobalite with those large volume changes. So you're right. If you have a silica refractory that has quartz present and you put it in a glass tank roof and you heat it up, it's probably going to disintegrate because of those large volume changes. So you have to get rid of the quartz and prevent those large volume changes.
Okay, cool. Thank you.
I have a question. For the previous slide, you talked about, you showed the transformation, the displace of volume change from quartz to tritamite was like 14, and from tritamite to cristobalite was 17, or is it from quartz to cristobalite?
Okay, yeah, maybe I didn't make that clear. From quartz to tritamite, it's 14.3, then from quartz to cristobalite,
Okay,
it's 17.2.
okay, that makes more sense, because when you showed the densities later on, it's like, well, tritamite and cristobalite are really close to each other.
Right.
And this 17.2, I was thinking that was between tritamite and cristobalite. Like, okay, got it now. Thank you.
It is a little confusing. Maybe I didn't make it clear, but it is quartz to tritamite and then quartz to cristobalite.
Okay, thank you.
So I think I showed this phase diagram when we talked about phase diagrams, but this is for SiO2, pressure versus temperature. Here's quartz, beta prime tritamite, and beta cristobalite, and then finally liquid. So these are the temperatures at equilibrium: 573 from alpha to beta quartz, 870 from beta quartz to beta prime tritamite. Beta prime tritamite can convert to cristobalite, 1470, and then finally it melts at 1723 degrees C. These points are triple points where we have three phases. So this point here is liquid, beta cristobalite, and vapor. And then this point here is alpha and beta quartz and vapor. And then the lines are two phases. So this vertical line is beta quartz and beta prime tritamite. And this line here is liquid and vapor. So any line represents two phases. And then below this line here, you have vapor, but these have to be extremely low pressures to vaporize these materials. And then one interesting thing here I briefly mentioned is metastable phases. So if you're in this phase field just liquid, and then you cool it down, you most likely will follow that dotted line. The liquid is going to remain as a glass. It's going to be amorphous. It's not going to crystallize. It's not easy to crystallize liquid SiO2. It's a good glass former. And then if you're in the beta cristobalite phase field, you may not transform to alpha. It may be metastable at beta. Then if you're in the beta prime tritamite phase field, you may not transform to the beta or the alpha form. So it may remain metastable. So all of the phases, whether they're stable or metastable, are all based on the same structural unit, tetrahedron of Si+4. It's coordinated with 4 O-2 ions. So all four corners of these SiO4 tetrahedra are shared, and they're bridging oxygens. So each oxygen bridges two of these SiO4 units. So the different crystal structures are just different ways of connecting these tetrahedra, and that's how you produce the different crystalline structures. If you have a glass, you still have these SiO4 units, but they're not arranged in any definite pattern, so they're random. So that's why you have an amorphous glass at that point. The bonding between Si and O is highly covalent. The electronegativity difference between oxygen and silicon is small. So you have these strong covalent bonds. So we can look at the phase diagram for SiO2 CaO. So a silica refractory runs about 97% silica and maybe 3% lime. And we just mentioned the lime promotes the conversion of quartz to either tritonite or cristobalite. So if you have 3% lime present at 1436 degrees C, that's going to produce 8% liquid. If you go to a little bit higher temperature, 1705 degrees C, that's going to make 8% liquid. And keep in mind that when you reach 30% liquid, you lose all volume stability in a refractory. You will lose the hot strength and you will lose the creep resistance. So this is the phase diagram for SiO2 and CaO. Here's 100% SiO2, and this is 100% CaO. And this one goes from about 800 to 2400 degrees C. So we're right over here, just a few percent lime. So here, as you heat it up, you see you have alpha quartz and wollastonite. Wollastonite is this calcium silicate, CaSiO3. And at 870 degrees C, theoretically you have tritonite, and these are equilibrium phase diagrams. So to construct a phase diagram from powders, you'd have to hold it a long time to go from quartz to tritonite. But from 870 to 1125, you have tritonite and wollastonite, this calcium silicate. And then 1125 to 1436, you have tritonite and another crystal form, pseudo-wollastonite. So there's a displacement transformation from beta to alpha wollastonite. Then finally at 1436, you're in this phase field tritonite plus liquid. And if you go a little bit higher, 1470, you're in this phase field liquid plus cristobalite. So you're over here at just a few percent lime. So you can actually use the lever rule to see how much liquid is present, but it's going to be a small amount. So the refractories are going to be fired in this temperature range here where you have a little bit of liquid present. Also, the impurities are important. Small levels of impurity in the silica refractory really hurt the high temperature properties. That's why they have to be relatively pure. So alumina is an impurity, TiO2 is an impurity, and they really drop the melting point of silica refractory. So if you have 5% alumina present, the balance would be silica, 95%. You'll develop 100% liquid at 1590 degrees C. If you have 10% TiO2 present, the balance being 90% silica, you're going to have 100% liquid at 1553 degrees C. So obviously that's higher than 30%. So these are going to lose all volume stability at these temperatures. So this is a plot of melting temperature, and it happens to be in degrees F versus percent of impurity. So here's alumina. So 3133 is the melting point of silica. So you're adding alumina, and you can see how the melting point drops. There's a eutectic at 2903 degrees F right here, and that's about 5% alumina. And then TiO2, you can see how the temperature drops. And there's eutectic at 2822 degrees F. Also on this diagram are sodium oxide and potassium oxide. And they lower the temperature even faster at smaller amounts. The temperature, the melting temperature really drops off with either one of these alkali. And they continue off the chart where the eutectic is for potassium, 31% K2O and 69% SiO2. That's the eutectic. It's down at 1385 degrees F. And then the eutectic for the Na2O and SiO2 is at 26% Na2O and 74% silica. That melts at 1460 degrees F. So any one of these impurities really hurts the high temperature performance of a silica refractory. So TiO2, Al2O3, Na2O, K2O, and sometimes Fe2O3, if that's present, are the common impurities. So if you have a combination of 1.2% of these impurities, you're going to develop 30% liquid at 1650 degrees C. So that would be a more of a conventional silica refractory. So the super duty silica refractory might be one at 0.4% fluxes. So a combination of all of these only at 0.4% gives you 10% liquid at 1650. So you can see 1.2% is not a high level of impurities, but it really affects the performance. So it's much better at a lower impurity level of 0.4%. So there's a factor here for silica. If you take the percent alumina and 2 times the alkali content, 2 times the sum of the Na2O and K2O, that gives you these different percentages. So if it's a conventional silica refractory, this factor will be greater than 0.5% impurities. If it's a higher performance super duty silica, it's going to be less than 0.5% impurities. So if you plot the percent liquid that forms versus the temperature, and in the bottom here it's in degrees F, in the top part of the diagram it's in degrees C, and it's 4.4% fluxes and 1.2% fluxes. So you see you go along here at, let's say, 0.4% fluxes, and you get to about 1650 degrees C, you have 10% liquid, but as you increase the temperature, you can see how fast this refractory deteriorates and how much liquid forms. And then 1.2% fluxes at 1650, you're already at 30 volume percent. And any increase in temperature really increases the liquid content. So high purity silica refractories will hold their hot strength and creep resistance and hold a load as long as you have very low flux content. They'll be pretty good to about 1650 degrees C. So this is a flow chart of how you process silica refractory. You start out with quartz, you crush it, and you screen it into different size fractions, and you use particle packing theory, put those size fractions back to produce maximum green density. And I have a course on processing refractories that talk about particle packing. But basically, you're putting back these particles of different size to maximize the green density. So those particles are mixed. You're adding your lime mineralizer, maybe 1 to 3% lime. Their dry press, so there's a small amount of water added, usually less than 5%. So it goes through a dry pressing operation. And then it's dried. There may be some type of organic binder added also for green strength. And then they're fired at about 1500 degrees C. So I mentioned it's a very slow firing schedule because of the large volume changes going from quartz to tridymite or cristobalite. So this is the heating cycle. You can see just going from room temperature to 500 C is 24 hours. Up to 1650 C is another 15 hours. 900 C is another 17 hours. Then 1100 C is another 10 hours. 1300 C is another 25 hours. Then a small increment, 50 degrees is 12 hours. And then 1410 is 30 hours. And then you're getting up to the temperature here where you're converting the quartz to either tritamite or cristobalite. So the long hold time is 30 hours, 20 to 24 hours. And then finally, there's a 2 or 3 day hold at 1430, 1480 degrees C to make that conversion take place. So now you should have all tritamite and cristobalite. And then you have to cool it down slowly because you're going through those displacive transformations. So this is the cool down schedule. Down to 800, it takes 22 hours. Down to 600, another 16 hours. And then when you're getting close to the displacive transformations, it's slowed down even more. 30 hours to 300 degrees, and then down to 150 is 30 hours, and below 150, 24 hours. Open means they're just opening the door to the furnace. It's a batch furnace operation. So very slow heating, long hold times, and slow cool down to make a silica refractory. So this is how the microstructure develops. The first diagram A, that's less than 750 degrees C. So nothing is really happening here. The temperature is too low. So you have large quartz particles in a matrix of the medium and the fine quartz particles, plus you have lime. So this would represent the edge of a large quartz particle. And so with this, these 3 finer particles are medium-sized particles. And they're in the matrix between the quartz particles, and then the small dots are the fine quartz particles and the lime. So basically A is as pressed, and then B, you're getting up to temperatures greater than 800 degrees C. Now the quartz and lime start to react, and it reacts on the particle surfaces. So on the surfaces of the quartz particles, the quartz and the lime start to react and start to form this lime silica glass. The reaction is much faster. The fines are disappearing and forming the lime silica glass. And when we get up to 1200 to 1300 degrees C, now the surfaces of the quartz particles, the coarser ones and the medium-sized ones, they're converting to cristobalite, and they're crystallizing from the glass, and then the matrix is cristobalite. Again, the finer particles are more reactive. And then when you get up to 1500 degrees C and D here, all the medium and fine quartz are now all cristobalite. So the X's here are the cristobalite, and the large particles of quartz, this reaction moves inward. They may not all be converted to cristobalite. The centers of these large quartz particles are still probably in the form of quartz, but their conversion to cristobalite is moving inward. The lime silica glass, as more and more quartz dissolves, becomes richer in silica, in D here. And then finally in E, now the tritamite starts to crystallize out. It's the same temperature, 1500 degrees C. So the surfaces of these particles are now being converted to tritamite, and the matrix is converted to tritamite. So typically in a quartz refractory, you're going to end up with tritamite and cristobalite. So the microstructures look like this. This is an SEM photograph, and just about all the microstructures I'll show in the course are ones that I've done over the 30 or so years I've been here at Orton. So this is a typical silica refractory. It's at 35x, so it's an SEM photograph at 35x, and we're using EDS to get the chemistry. So the chemistry of this entire field of view is over here. It's about a 97% silica refractory, is about 1.7% lime. And then you have alumina, iron oxide, and sodium oxide adding up to a little more than 1%. So refractories are typically 15 to 20% porosity. So all the black regions are the pores. The dark gray regions are the silica crystals. So that's basically 100% silica. And then the light gray is where the lime and the impurities are concentrated, basically at the grain boundaries. So this light gray region was analyzed. It's about 78% silica, and the lime is concentrated there, so it's about 15% lime. And then you have alumina, iron oxide, sodium oxide, potassium oxide, titanium, magnesia. These are the impurities that are concentrated in that region. So that's the glassy phase at high temperature. So now we go up to 750x. You can see all the silica crystals here. The grain boundaries are in black, so they're easy to see. If you analyze any of these crystals, it's about 99% silica, and the balance on this particular one showed up as 0.5% alumina. And then here's your impurity region. There's actually two phases here. The overall chemistry of this region is about this one, about 60% silica, 28% lime. And then the balance are the same type of impurities: alumina, the iron oxide, the two alkalis, sodium and potassium, titanium, magnesia. So there's actually two phases here because this is cooled down to room temperature. The white phase, it's crystals of that phase I mentioned, wollastonite, the calcium silicate. And then between the crystals are this darker gray region. So the crystals are light gray. The darker region is the residual silica-based glass. So besides doing EDS analysis on either regions or points, we can do an EDS mapping. So the yellow is SI. So the bright yellow is where all the cristobalite and tridymite crystals are. And then the region where the impurities are concentrated, you can see some yellow. It shows up a lot less intense. This is very intense because it's basically 100% silicon. And if you map the mineralizer lime Ca, it's in purple here. And it's at this point, it's concentrated in those crystals of wollastonite. And you can also map the aluminum well, this is in purple for the lime. The alumina is orange. It's basically concentrated in the glass matrix. Here's the sodium. It's also concentrated in the glass matrix. That's in blue. And then the iron is again concentrated in the glass matrix. That's in this kind of a red-orange color. So the impurities are concentrated in the grain boundary regions. And there are two phases present: cristobalite plus a high silica glass. So when you finally fire this material, you're going to end up with 30 to 60% tridymite, 25 to 50% cristobalite. You don't want any quartz present, so it has to be less than 2% to be a viable silica refractory. Glass, maybe 5 to 25%. And then that crystalline phase, wollastonite, CaOSiO2, the calcium silicate, 1 or 2%. So a few key properties, thermal expansion. You have quartz, cristobalite, and tridymite. All of these have these displacive transformations. So the thermal expansion turns out to be high at low temperatures, and I'll show some diagrams for this, and low at high temperatures. There's a unique crystal structure has some open areas or open volumes that allow the vibrations of the atoms to move into those volumes to give low expansion at high temperatures. So the thermal shock resistance is going to reflect the thermal expansion. So thermal shock resistant materials have low thermal expansion. So when you look at quartz, cristobalite, and tridymite, you have these displacive transformations. Volume changes are on the order of 1 or 2%. So if you go fast through any of these transformations, you're going to cause some damage. So the thermal shock is poor at low temperatures, and we're basically saying 700 degrees C is a low temperature. That's where any of these transformations take place, the displacive transformations. So you have to heat slowly in those temperature regions. But when you get above that temperature, you no longer have displacive transformations, and you have a material that has very low thermal expansion. So if you're cycling a material, silica refractory material at a temperature greater than 700 degrees C. So if you're cycling above 1700 degrees C, it's going to have good thermal shock resistance. If you're cycling below, 700 degrees C, rapid changes in temperatures, it's going to give poor thermal shock resistance. So this is density versus temperature, and this is density. As you go up, the density is decreasing. So this is quartz, this is cristobalite, and then the top curve is tridymite. So there's a thermal expansion that corresponds to a density and decrease. So as you go up in temperature, the density is decreasing, it's expanding. And here's your displacive transformation from beta to alpha quartz. And you can see as you increase the temperature, it's pretty flat. So the volume isn't changing that much. The density isn't changing. So cristobalite has the transformation right here, alpha to beta cristobalite, much lower density, and then it tends to level off at high temperatures. And then the tridymite, alpha to beta 1 to beta 2 is right here, lower density, and then it tends to level off at higher temperatures. And we're looking at temperatures, I said 700, so that's right about here. So these are the density changes for the displacive transformations for quartz, cristobalite, and tridymite. And then these vertical lines are the volume changes for the reconstructive transformations from quartz to either cristobalite and tridymite. So this is tridymite, this is cristobalite. And again, 870 is the prediction from thermodynamics, but kinetically, it really happens at a higher temperature. So those are our summary of the volume changes and the density changes. We just look at specific volume in cubic centimeters versus temperature. Here's quartz. Here's your volume change, your displacive transformation. Here's cristobalite and its displacive transformation. And then the two displacive transformations for tridymite. And if you go from quartz to cristobalite or tridymite, you can see these large 14, 15% volume changes. The important thing is above 700 degrees C, these start leveling off. So this is an actual thermal expansion versus temperature curve. for 4 different silica refractories, A, B, C, and D. In this area, you have the tritomite and cristobalite displacive transformation, so you can see the rapid increase in the expansion in that region. And here you have the quartz transition, 573 degrees C, and you can see in 3 of the materials, B, C, and D, you have a rapid increase in thermal expansion due to the phase transformations. These are the specific gravities for A, B, C, and D. A is the smallest, D is the highest, and in between is B and C. So if you're running a quality control check on a silica refractory, you can measure thermal expansion. You do not want any quartz present. So B, C, and D, you can see the quartz transition, but A has been converted completely. So there's no quartz transition there. So if you want to check the conversion from quartz to cristobalite and tritomite, you can run a thermal expansion. You don't want to see these rapid changes at 573 degrees C. Or you can measure the specific gravity. Since tritomite and cristobalite have the lower specific gravity, if you're in this region, 2.32 grams per cc, that's probably going to be complete conversion from quartz to cristobalite or tritomite. But D is only 2.52, so it's got a much higher specific gravity, which means you still have quartz present. So if you look at D here, you can see how much quartz is present, and you can actually calibrate these increases at 573 degrees C. You can calibrate it and sort of get the percent quartz that's still in this structure. So A would be an ideal thermal expansion for a silica refractory. So this is a plot of linear expansion. This is inches per foot, and it goes up to a 1/4 inch per foot. And this is linear expansion in percent. The bottom is temperature in degrees F. The top is temperature in degrees C. So we'll go over all of these refractory compositions in this course, but silicon carbide is covalently bonded. It's got a very low thermal expansion. Well, not very low, but it's the lowest of the refractories. The lower the thermal expansion, the better the thermal shock resistance. The highest material in terms of thermal expansion is MgO. This happens to be a 92% MgO refractory. So you heat MgO up to about 1450 degrees C. It'll expand a 1/4 inch per foot, whereas silicon carbide is less than 1/8 per foot. And in between, there's various aluminum materials. Going up in alumina content increases the thermal expansion. Phosphorite is a magnesium silicate. But here's a silica refractory. You can see in this low temperature region the displacive transformations, the cristobalite and tritomite transformation. So there's a rapid increase. And then because of the open structure, you have very little change in size. So the thermal expansion tends to be rather flat. So here, if you put this refractory in a furnace, you have to heat up slow in this region, and you can go faster in this region. So if you're cycling, rapidly cycling the temperature in this region, you're going to have a great deal of problems because of the expansion change. But up in this region here, you can cycle this refractory. If there's no thermal expansion, it doesn't build up any thermal stresses, and you don't have any thermal shock issues. So silica is unique in that it's got this flat behavior, and it has good thermal shock resistance above about 700 degrees C. So silica refractories have hot load. So they have good strength at high temperatures. They can hold the load. They have good resistance to creep deformation. And if they're high purity, they can carry this load to within a few degrees of its melting point. So 1650, if it's high purity, it can hold a load easily of 50 psi. Creep deformation tests are usually run at 25 psi. And silica is an acidic refractory. And if you put it in contact with an acidic slag, it's going to have excellent corrosion resistance. And again, there's another course that goes over properties. I guess it's the third course in the sequence, and it'll go over strength and creep resistance and corrosion resistance. But if it's an acidic refractory, it's going to hold up against acidic slags. You're not going to want to put a silica refractory in contact with a basic slag. So the fused silica I mentioned has low thermal expansion, 0.5 times 10 to the minus 6 centimeters per centimeter degree C. That's really low. MgO, I showed MgO on this diagram. It's way up here. That's about 13 times 10 to the minus 6 centimeter degree C. So this is extremely low thermal expansion. The problem is above 1,000 degrees C, it starts reverting back to cristobalite and trinamite. That's unfortunate. We don't have any refractory materials with these low thermal expansions. Back on this diagram, silicon carbide is about 4 or 5 times 10 to the minus 6. MgO is about 13 times 10 to the minus 6. And then fused silica is 0.5 times 10 to the minus 6. So this material, if you thermally cycle it in this region here where it's still amorphous, has excellent thermal shock resistance. So good thermal shock resistance for fused silica up to about 1,000 degrees C. Unfortunately, when you go above 1,000, especially when you hit 1,200, you crystallize cristobalite. So if we look at the thermal expansion of a silica refractory versus fused silica, this is percent linear change, and then versus temperature. And there's a whole range of refractory compositions on this diagram. So this is the crystalline silica refractory. It goes through the displacement transformations and then has this flat behavior. But this is where fused silica is. It's number 19 here. It's this low. So these are all refractory materials from your carbides and nitrides, the lowest expanding up to the MgO type base materials up here. And then in the middle are your alumina and zirconia refractories. But you can see how low fused silica is. It's just not a high temperature material. And this fused silica is actually added to a lot of the composite refractories, which we'll talk about. That'll enhance its thermal shock resistance. So the last slide I have here, some of the key properties. Coke ovens. So silica refractories are commonly used to line coke ovens and the roofs and glass tanks. So bulk density is usually pounds per cubic foot. These are the bulk densities, 110, 105, 119. The porosities, typical in the 15 to 20, 25% range, 23 and 28 here. This is a little lower. It's a glass tank refractory. You don't want a whole lot of porosity there because that leads to more surface area and higher corrosion rates. These are the parent-specific gravities in grams per cc, and the cold crushing strengths and PSI. So this has less porosity. It's going to have a higher cold crushing strength than this one. So 18% has 12,000 PSI, and 28% has 4,000 PSI. So these are typical cold crushing strengths. And then the silica, these are all about a 95, 96% silica. You can see there's all about 2.5, 3% lime present. And these particular refractories had some alumina and iron oxide impurities. The fused silica refractory is a refractory that's based on, you take the silica glass, you crush it, you make a particle size distribution, and you sinter it. So it has porosity. These are sometimes used to line coke ovens. And this one is a pretty high purity, almost 99% silica. So that's what I have on silica refractories. The next two classes will add alumina to silica and go over all the alumina silica type refractories. It's quite a large number of different possibilities. So it'll be 2 lectures. I guess the first lecture will probably mostly be the low alumina content fire clays, and then the second lecture will probably concentrate on the higher alumina refractories. So that's what I have. Have a good rest of your day, and I'll see you on Wednesday again. Again, thanks for attending.
Thank you.